Have you ever really stopped to think about how you're seeing, well, anything right now? It feels instant, right? But what if I told you it's actually the very last step in an absolutely incredible journey? Today, we're going to follow a single ray of light, from the moment it's born to the moment it hits your eye.
All right, to get our heads in the game, let's solve a classic mystery. You're watching a storm. You see that huge, brilliant flash of lightning. Bam! Instant. And then you wait. 1, 2, 3, and then boom! The thunder finally rolls in. We know they happen at the exact same time, so what gives? Well, it all comes down to a cosmic drag race.
And here's why it's not even a fair race. Take a look. Sound. It's moving at a pretty respectable 330 meters per second. But light? Light is blazing along at 300 million meters per second. It is just no contest. The light from that lightning bolt gets to your eyes pretty much instantly. Meanwhile, the sound of the thunder is literally still pushing its way through the air to get to your ears.
Okay, so this lightning-fast thing, our messenger, is called light. But what is it really? To understand its journey, we first need to get a handle on the basic rules it has to follow.
Rule number 1, and this is a big one. Light is the fastest thing in the entire universe. That number right there, 300 million meters per second, that's its top speed, the absolute speed limit of the cosmos, which it hits in the vacuum of space. And when I say nothing is faster, I mean nothing.
But it's not just about speed, it's about how it moves. Light travels as a transverse wave. You can see it here. It means as the energy moves forward, the wave itself wiggles up and down, kind of like ripples on a pond. Sound is totally different. It's a longitudinal wave, which is more like pushing a slinky back and forth.
So let's quickly recap the 3 golden rules for our little light ray. First, it travels in perfectly straight lines. This is super important, as you'll see in a minute. Second, it's a transverse wave. It does the wiggle. And third, it doesn't need any stuff to travel through. It can just zoom right across the empty vacuum of space. That's why we can see stars that are billions and billions of miles away.
So, light is this speedy, straight-shooting wave that can travel through basically nothing. But what happens when its journey is interrupted? What happens when it finally runs into, well, something? That, my friends, is when the real fun begins.
Turns out, when light hits an object, there are really only 3 things that can happen. It can pass right through, it can get scrambled on its way through, or it can be stopped dead in its tracks. Let's look at each one.
First up, you've got your transparent materials. Think of a super clean window or a glass of water. Light just sails right on through, no problem. The path is clear, and that's why you can see a perfect image on the other side. Our little messenger gets a total free pass.
Next, we have translucent stuff. This is like frosted glass or a piece of wax paper. The light still gets through, but the material scatters all the rays, sending them in a million different directions. So yeah, you can see that there's light, but the image is all blurry and distorted. The messenger gets through, but it gets a little roughed up along the way.
And finally, we have opaque objects. And this is most of the world. A wooden door, a book, your coffee mug. Opaque objects don't let any light through at all. The light either gets absorbed, usually turning into heat, or it bounces off. It reflects. For our messenger, this is a dead end. It either gets captured or it's forced to turn around.
Okay, so we know what light is, we know its rules, and we know what happens when it hits stuff. Now it's time for the main event. Let's put all the pieces together and figure out how this incredible journey ends with us actually seeing things.
Let's make this real. Picture it. You're outside on a beautiful sunny day, and you're looking at a flower. Now, that flower isn't a tiny lamp. It's not making its own light. So how in the world are you able to see it?
And here is the absolute key to everything. Some things in the universe, like the sun or a light bulb, are luminous. They give off their own light. But most things, like that flower or the moon or this chair, they're non-luminous. They don't make any light. The only reason we can ever see them is because they act like mirrors, reflecting light from a luminous source.
So check it out. Here's step 1. A ray of light travels 93 million miles from our luminous source, the sun. It travels in a dead straight line, and it hits our non-luminous object, this beautiful rose.
And here it is, the magic moment. That rose is an opaque object, right? So it can't absorb all that light. Instead, it reflects it. It bounces that sunlight off in all directions. And some of those reflected rays travel in another straight line, right into your eye.
That's the secret. You're not actually seeing the flower. You're seeing the light that has bounced off of the flower. That's what seeing is. Okay, now that we've got the basics down, we can explore some really cool side effects that happen simply because light follows these rules so strictly.
Hey, remember that first rule? Light travels in straight lines? Well, what happens when an opaque object, like this tree, gets in the way of those straight lines? You get a shadow. A shadow isn't a thing. It's not made of anything. A shadow is just a place where light isn't. It's an absence of light, created because the straight traveling light rays got blocked. Simple as that.
We can actually use these same rules to build a camera, a really simple one. A pinhole camera is basically just a box with a teeny tiny hole in one end. Now, because light only travels in straight lines, rays from the top of an object have to travel downwards to get through the hole, and rays from the bottom have to travel upwards. They literally have to cross over.
And the result of this crossover is kind of wild. The light from the top of the object hits the bottom of the screen inside the camera, and the light from the bottom hits the top. So what you get is a perfectly clear, but completely upside-down image. And get this, this is almost exactly how your own eye works. The lens in your eye projects an inverted image onto your retina, and your brain just automatically flips it right side up for you without you even noticing.
So, look, if you take only one thing away from our entire journey today, please let it be this. From the very screen you are watching right now, to the faces of people you love, to the moon in the night sky, you're only seeing them because they are reflecting light into your eyes. That's the whole ballgame. And I'll leave you with one final, mind-bending thought to chew on. We know light is incredibly fast, but space is just unbelievably fast. It actually takes light a full 8.5 minutes to travel from the sun to us here on Earth. That means when you look at the sun, don't actually stare at it, of course, you're seeing it as it was 8.5 minutes in the past. You are literally looking back in time. So that begs the question, are any of us ever really seeing the world as it is, right now?